Hello everyone and welcome to this section. In this section we're going to train a simple perceptron network that we actually built before, and we're going to see how can assess the performance of our network. Okay, all right, so again I'm going to walk you through a quick overview of what we have had before. Again, all these codes up to this moment, this step, basically we have done it before. I'm just going to go through it. We're going to import all our libraries. So that's the first step. So let's run it. And then the next step is that we're gonna load the data. All right, so we loaded the data. We actually took a look at the data. So we have again our two inputs and our speed, which is our target class. And then we plotted the data here, as you guys can see. How can we decide, if the truck we're gonna drive, fast or slow? Let's keep going. Here again, we loaded, the X train. So X train has two columns, right? And then we have again Y train as well, which is only have one column. All right. And then the next step is that we started to build our network. So we build just one single neuron network. So we have two inputs and we have one neuron, right? So here we have our input dimensions is 2, our activation function is sigmoid, and we did what we call it the dense to add, the network in a sequential form, a sequential way. Okay, so up to this moment, we actually discussed it. Here, okay, let's add these two lines that can be used for training. So what we do afterwards, we do what we call it model, compile, and then we use the loss function, okay, which we'll call it binary cross entropy. We use binary cross entropy because we only have, one output that has a binary value, either 0 or 1, okay? There's binary categorical, for example, entropy. We're gonna use it moving forward if we have different categories, for example, and so on, okay? Okay, so here we're just gonna use the binary cross entropy as a loss function. And then the next one, we're gonna use the optimizer, gonna be Adam optimizer. Again, I tried to copy a couple of, you guys can go ahead and search for Adam optimizer, but Adam is kind of a specialized form of our backpropagation. It relies on the backpropagation the same way or the same fashion. Again, it calculates the gradient and it does what we call a gradient descent algorithm to train the network, but it's in a kind of specialized form, okay? I'm not gonna go again into the details of the Adam optimizer, but it's very powerful optimizer that we can use to train our artificial neural network, okay? So that's pretty much it. The next step is we're gonna do model.fit, which is this command. And then we're gonna use, okay, first of all, what our training data. So we have our X train, that's our training data. And we have our target class, which is Y train. And then we're gonna specify how many number of epochs. So we have 100 epochs. And here verbose, which is how many, what details we wanna plot as we go, okay, now as we start training, okay? And that's pretty much how can you fit or how can you train our network in a nutshell. Obviously behind all this, there's a lot of mathematics, a lot of equations, a lot of stuff in the background. But the whole idea is, as we mentioned before, the intuition. We have input, we have output, we calculate the error, we go back, we update the weights in a certain fashion. All right, let's run this. And actually the model is running. As you guys can see here, these are the number of epochs that we showed you, which is how many times we actually show the training data, and we'll go back and update the weights. As you guys can see, the loss is going down. This is going down. We reach let's say 0.28. Okay. All right. Let's take a look again at the model summary. We showed that before. So we have 3 tunable parameters, 2 weights and 1 bias. All right. And the next step is that, okay, now our network is fine. Okay. Let's go and predict, or let's assess, for example, the accuracy of our training data, okay? The key element here is that we didn't divide the data into training and testing, all right? This is, again, a very simple example. We didn't do any divide. We used the entire data to train, and here we want to assess the actual training as well, using the exact same training data. In general, I don't want you guys to be confused. This is just a very simple example, okay, using one neuron, just to show you how can we build something from scratch. Moving forward, the next exercise, actually we're gonna take the data, we're gonna go do the right thing. We're gonna, first of all, develop a multi-layer perceptron network, and we're gonna actually take the data, divide it into train and test. Here, it's a very simple, plain example. We use the exact same data. We didn't even divide it at all. And that's, just to give you if you guys not familiar with Python, if you're not familiar with programming in general, I don't want to show everything at once. Here we're just gonna build it step by step. So here what we're gonna do is we're gonna do model, okay, which is our trained model right now. We're gonna use what we call it predict classes, and we're gonna use the X train. Okay, so let's predict. So simply here you are doing a forward run through the network, and the network will give me its prediction, which is Y train predict. All right, okay, let's run it. Okay, that's good. All right, so the next step is that we wanted to, okay, let's assess the performance of our network just for the training data set. So what we're gonna do is that we're going to use from sklearn, okay, we're gonna use the metrics, all right, and within that matrix, we're gonna import what we call confusion matrix. If you guys recall, we discussed the confusion matrix before. It's again one-stop shop that can shows us all the correctly classified samples and all the misclassified samples. And then what we do is that we call confusion matrix, and then we pass along our ytrain, which is our simply our true labels, and our prediction, which is ytrain predict. Okay, the confusion matrix will return CM, and then we're going to use the Seaborn heat map method within the Seaborn library to actually plot again the CM, okay, which is our confusion matrix, and then annotation true, which can be used to actually plot the number, the total number of classes within the confusion matrix. And let's get started. Let's run it. Let's see what's going to happen. All right, it actually looks pretty interesting. So here, as you guys recall, we had 1,000 samples, and here the network has correctly classified 500 here. Okay, the class was 0, the true class was, the prediction was 0, and the true class was 0, which is good. And then the network correctly classified 498 samples as well. However, it misclassifies 2 samples. Okay, that's basically the error that we've got out of this network. Okay, that's pretty much how can you view the confusion matrix. The only problem here, obviously, this is kind of, you know, type 2 error. Okay, and we try to avoid type 2 error at all costs, as we mentioned before. But again, this is kind of like a very simple example, and we didn't even run, we didn't even use the testing data set, and we didn't even run any advanced, you know, multi-layer perceptron network. Okay. The next step to visualize the results is to kind of use kind of what we call it a mesh grid to visualize the results. Again, it's kind of, you know, if you guys don't even want to like go through all that code or write that code, you can again utilize it or use it, you know, whenever you want to show you a visual representation of, okay, these are the 2 classes. Where did we draw our decision boundary, or where did we draw our, you know, kind of line that you know, like separates the 2 classes together? Okay. So what we did here is we're going to create kind of a grid. So they're going to create what we call the mesh grid, all right? And what we're going to do is that we're going to get kind of a grid using the data, the X training data that we have. So here we just define the start point, the stop point, all right? And that will return, again, we're going to do that as well for the second step here too as well, all right? And that will create our kind of mesh grid for our 2 samples, for our 2 inputs, which is X1 and X2. Okay, since we have 2 inputs, that's why we have done it kind of, you know, for 2 inputs. And then next, we actually do the actual prediction. So that will actually give us my prediction. These are predicted values. Okay, and why? Because we want to show the actual true values along with the predictions as well on one graph. All right. That will contour F will simply plot our contour. I'm going to show you as well how does it work. And then here we just want to specify the color maps to red and green, which is, you know, kind of to show us, okay, how many samples were truly classified and how many samples were misclassified. And then we limit simply the x-axis and y-axis to the minimum and maximum values of x1 and x2, which is our 2 inputs. And then afterwards, we actually do use a scatter function, okay, which is plot.scatter, to actually tell us, okay, where are the true values and where there are, or the correctly classified samples and misclassified samples. All right. So let's take a look and let's run it. And that's that's very interesting. So as you guys can see here, that's my first class and that's my second class. And you guys can see that's kind of the boundary that we had in between. Okay. Which means that the network, even with just one layer, with just one neuron, was able to adjust the weights in a way to draw that boundary and classify the 2 classes. Again, this example is very simple, very easy. Moving forward, we're gonna have way more complex and way more complicated examples. All right, okay. The next step is, okay, let's view the weights and let's view the biases. As we have done before, we have done it before for an initialized weights and biases that, you know, weren't trained. Now we actually have a trained network, so obviously you will see different numbers. So if we run the weights and we run the biases, you will get different numbers. The bias, if you guys recall before, was 0. Here, actually, the network had to adjust the bias to 2.2. Here we have the weight 1 minus 3.2, weight 2 minus 2.1. And pretty much, if you guys think about it, if we assume that, let's say, our activation function is in a way like linear form in a way, okay, it's kind of the equation of or the model of that line in simple form. we have two weights and we have a bias. It's very simple equation, linear equation that can tell us, okay, that's the equation of a straight line. You can use it, for example, using regression, but here we actually use an artificial neural network, which is, kind of an overkill here in this example. But again, we use just one neuron to classify these two classes, all right? That's pretty much all what I have for this section. I hope you guys enjoyed it, and see you in the next section. Hello everyone, and welcome to this section. This section, we're going to take our just one neuron model that we had before, or the perceptron model that we had before, to actually take it to the kind of a next level to build multi-layer perceptron network, okay? So I actually showed you that before, but if you guys go to the playground, the TensorFlow, you can actually go there and try to change, for example, the number of hidden layers, number of neurons, and that's what we're going to be doing in this section. We're going to add, again, different hidden layers. We're going to add different neurons. We're going to change, for example, the activation functions from sigmoid to like ReLU or whatever. And then we're going to use it to actually classify more advanced data sets. All right? Again, I urge you guys to go there. We have done it before. This is just kind of, a refresher of what we have done and how we actually train it and get an idea of how we train our model. Okay? All right. So let's, again, take our network, which is, again, single neuron network. Okay, that's one neuron. And let's build what we call it the two neuron network, or two neuron model. Again, step by step, let's go and see how can we build the entire network. So as you guys can see here, this is one neuron. So we have a bunch of inputs, P1, P2, P3. We have a series of weights, weight 1, weight 2, weight 3. We knew right now that we can multiply the inputs by the weights, add a bias signal, and that will generate, let's say, signal, let's say A1, okay? And then, that will generate N1, which is this value, which is N1. We'll apply an activation function F, that will generate our, let's say, A1, or we call it Y, or we'll call it whatever, okay? That's the first neuron. Okay, let's get another neuron. That's another neuron. It's exactly the same, okay? We use the exact same input, P1, P2, P3, and we have the output going to be A2, all right? So these are kind of two neurons like separately, right? What we want to do, then we're actually going to combine them together and build our first kind of, two neuron model, okay? So since the inputs are common, so P1, P2, P3 are common, if we combine them somehow, actually we're going to generate this kind of, the two neuron model. So the input P1 will actually be sent to the first neuron and the second neuron. And the weight value, that's very important. It's what we call it weight 1, which is weight that's going from the first input to the first neuron. And then we have what we call it weight 2, okay, which is weight that's going from the first input, 1, to the second neuron, 2, okay? And then the next step is we're going to call it P2, which is simply, again, we read it kind of, in a reversed fashion, all right? So we have P2, okay, going again to the first neuron, and we have 2 going to 2. And then here we have 3, okay, going to 1, all right? So we have input 3 going to 1, which is weight 1, 3. And then we have weight 2, 3, all right? And then we have a bias. We have bias 1 and bias 2. We apply again activation functions, generate A1 and A2. So in very simple form, okay, in order to draw, all this like network, what we're going to do instead, we're just going to represent everything in a matrix form. And that's the beauty of it. We can actually just boil down the entire network to become just a couple of weights that tell us exactly how can we train it. We can apply different, more advanced training algorithms moving forward. And that's pretty much the matrix representation of our network, of our neural network. So if our neural network in this case, okay, first of all, has 8 adjustable parameters. Why? Because we have 3 weights for the first neuron, 3 weights for the second neuron. So we have in total, we have 6 weights, right? And we have 2 bias signal. Okay, that's again, if you count them, again, it's very simple. 1, 2, 3, 4, 5, and 6. That's 6 weights here. And we have 2 biases that will sum up with 8 adjustable values. So now we can have simply 2 matrices. We can represent the entire matrix, the entire network in 2 matrices. Matrices of biases to B1 and B2. And we have matrices of weights. So we have weight 1, 1, weight 1, 2, weight 1, 3, 2, 1, 2, 2, 2, 3. And then we can simply perform like a matrix multiplication. Multiply the weights by the inputs, okay? Add the bias signal, apply an activation function F, you're good to go. That's it. That's how you represent a 2 neuron model in a matrix representation form. All right. So now we're good. We went from 1 neuron to 2 neuron. Let's take it to the next step. Let's actually build the multi-layer perceptron network. That's pretty much what we have here. So we have our input layer. We have our different hidden layers. We can have as many hidden layers as you want. Okay. And again, the multi-layer perceptron network consists of one input layer, hidden layer, and one output layer. And again, all the inputs propagates through the network to generate our output. All right. Okay. So let's take a look at a little bit of math for the multi-layer perceptron network. So as you guys can see, if we pick any of these neurons, again, you will see a bunch of inputs going to our neuron. So we have, let's say, x1, x2, x3, for example, multiplied by a set of weights for this neuron. The neuron will generate an output, okay, x. Okay, and again, I don't want to dig into all, because we're not going to be doing any of that math. Again, I'm just going to give you the intuition of what it is. Like, how can we boil that network down to just, a couple of matrices. So here we simply multiply all the weights, okay, by the inputs x in any neuron. If you pick any neuron, we have inputs, we have weights, multiply them together, apply an activation function here. This is our activation function to generate simply the x, which is going to be the input to the next layer, all right? And that's why here you will see there is n plus 1, which is, for the next layer represent until we generate the actual output from the network, okay? Activation function here, we assume it's sigmoid function, for example. So it's 1 divided by 1 plus e power minus the input. And that's kind of the nonlinear sigmoid function. All right, so let's take a look at the matrix representation then. That's pretty much the matrix representation. We have a couple of inputs, P1 up till Pn1, which is the number of inputs that we have. And then we have a couple of weights. So we have series of weights. So if you have weight 1, 1, weight 1, 2, and so on, that's how we kind of build our matrix, and that's how we use it for backpropagation or for any training algorithms to actually train our network. Okay, all right. And you guys can go to this, check out this like research paper. It can shows you all the how can you build an actual artificial neural network, and that's where the image is actually from. And if you guys can see here, that's again m small. That's the number of neurons for the hidden layer, and n1 that's number of inputs. Okay, all right. That's how can we build from a single neuron model to a 2-neuron model, and then to a multi-layer perceptron neuron model. Okay, what we're going to do now, we're going to actually use all that learning in Python or in the Jupyter notebook to actually build our multi-layer perceptron network. All right, that's all what I have for this section. I hope you guys enjoyed it, and see you in the next one. Hello everyone, and welcome to this section. In this section, we're going to build our multi-layer perceptron network. And instead of using just the two simple data sets that we had before, which is kind of, two classes that are really far from each other, which is very easily used, like we can easily use one perceptron or just a single neuron model to actually classify these two classes. What we're gonna do here, we're gonna use a little bit more challenging data set, all right? Again, all these data sets kind of, like artificial data set, and I'm going to show you even how can we generate that data set, okay? All right, so let's get started. So first step is we're going to import, again, pandas as PDs, NumPy as NP. We're going to import matplotlib and Seaborn as well, okay? I hope you guys are experts by now with this. Second step is that what we're going to do is that we're going to create our what we call a two-moon example, which is a little bit more challenging. The data which will look like this in a way. The classes are kind of like interacting with each other a little bit more. They're way more closer to each other, so it's kind of more challenging problem compared to the other problem that we had. So what we do, we can use sklearn. So from sklearn, we're going to import the data sets. Okay, so we can use data sets to generate whatever data we want. Here we want to create the moons example, or the moons data set, which is very famous data set. So again, from sklearn imports data set, what we're going to do is that we're going to call again data sets dot make moons to create our moons. And here we're going to specify how many samples do I need. So I'm going to specify 1500 samples. And the noise, let's say, is 0.05, for example. Okay, and that will generate the data here in noisy moons. All right. Okay, let's run it. So we're good. What we're gonna do, we're gonna take noisy moons, and then we're gonna specify our input and output. If you guys recall, we had our X, which is gonna be our input, our neural network, and our Y, that will be my class, okay? Which color or which class it is, okay? If when you say class, again, I want you guys to go back and link it to our truck example, okay? If you wanna say, let's say, the first class is driving fast or driving slow, that's pretty much all the decisions that we need to take, okay? All right, let's run it. So now we have X and Y. Next step is we're gonna use plot.scatter to plot simply our X versus our, the first two, mainly the first two inputs. So X, we have two columns, which is our two inputs. And we're gonna use Y to simply specify our hue in a way, or our two classes, okay? That's why we specify the C will be equal to Y, which is simply our target class, all right? So let's use it, let's plot it. Okay, that's pretty interesting. So as you guys can see here, that's my data right now. So I have kind of two inputs, X1 and X2, and I have two classes. That's my first class, color yellow, and that's my second class, all right? Okay, perfect. The next step is, what we're gonna do is we just bear in mind before we dig into the next section that the data here is not normalized. One data range, for example, from minus 0.5 to 1. The second data is would range from, let's say, from the second feature, for example, range from minus 1 to 2. All right, that's in general adds problems when we do training to the network. What we love when we do training is we have what we call it normalization, or we call it feature scaling. Okay, we wanted all the numbers, for example, to range, let's say, from 0 to 1. Okay, so we don't need to have a feature that, let's say, range, let's say, in thousands, and the other one we're going to be in 0.1, or let's say range from 0 to 1. We don't like this. We want all the features, okay, to be, let's say, we call it normalized or scaled. Okay, all right. So let's move forward. So what we're gonna do here is, again, we're gonna import our keras. We're gonna do our sequential and our dense, and actually make blobs. These two, we're not gonna use them in this section. We're gonna use it actually in future sections. All right, so let's run it. But what we're gonna use is what we call it min-max scaler. So min-max scaler, that can be used from sklearn.preprocessing, which is simply used to, again, do all our feature scaling, okay, which is, again, make the network, or make the input data range from 0 to 1, as I'm going to show you right now. The next step, which is, we haven't done so far, is we wanted to take the data, okay, and divide the data into training and testing data, all right? Again, if you guys recall, we're going to use the trainings portion to actually train the network with various number of epochs. And after the network is trained, we're going to use the testing data set, which is data set that the network hasn't seen before, to actually test our trained network, okay? The key element is to test our network if it's able to generalize or not, which is a very important element. How can we perform, how the network can be able to generalize the data, all right? So in order to split the data, I can simply go, because we have kind of two arrays per se, we can just go and try to, find the specific section. Luckily, all these stuff are, very easy to perform. What we're going to do, we're going to use, again, sklearn is very powerful. We're going to use from sklearn, okay, dot cross validation, all right, import, we call it train test split, okay. And then afterwards, we're going to use train test split. We're going to pass it along our X, our input, our Y, our test size. So here we're going to use 25% for testing and 75% going to be used for training. And random state, you guys can use it here, for example, 0, to get my exact same results that are going to be getting, okay? If you guys, use, let's say, whatever, 101 or whatever, random state, then you're going to get different results than what I'm getting, okay? And then afterwards, this basically we're going to return back to us our X train, our X test, our Y train, our Y test, which is simply divided for us, again, 25%, 75%, which is going to be perfect. All right, let's run this. Okay, we look okay. And then the next step is, what we're going to do is we're going to do the feature scaling. Again, we're going to use, here we imported the min-max scaler. Actually, what we're going to do is going to actually copy this, put it here, so you guys can, I'm going to include it as well in the final notebook. So again, we're going to do, we're going to run it. Let's walk you through it first. So we're going to load, again, min-max scaler. So we're going to define a scaler first, so that we're going to min-max our min-max scaler first. Second step, we're going to apply a method, let's call it fit, okay, on our X train data, okay. And then the next step is we're going to use a transform. So we're going to use scaler.transform on the X train. and that will give me backwards my X train scaled, which is simply, that's my scaled features or my scaled inputs, which is going to be ranged from 0 to 1. I'm going to show you as well. We're going to plot it here to show you that what we meant. We're going to do that again, the exact same thing. We're going to do it for training. We're going to go back here and do it for testing. All right. And then here, I'm going to use the exact same command that we did to plot the plot scatter. We're going to use the exact same thing, but to plot our scaled features or scaled inputs. So here our X underscore train underscore scaled, that's simply our return function from here. We're going to return again we're going to plot the first, again, column 0. That means we're going to plot the first column, okay? All the rows and the first one, which is 0. And then we're going to plot all rows again, but the second one, okay, or the second column, which is my X2, basically. And then again, we're going to use Y train to be used for color detection, or just give me my target class, just to show which target class it is. Let's run it. Okay, and it looks perfect. Now, if you guys notice that we have the exact same shape, so it's actually exact same shape, but the values here, instead of 2, we're actually having it 1, which means we actually scale the feature now, or scale the input. So we have my input 0 to 1, here my input as well from 0 to 1. All right, let's build our network. What I'm going to do here, I'm going to kind of run 2 runs. We're going to use the exact same network that we had before, which is the single perceptron model or 1 neuron model. And let's assume that, okay, we're going to pose like way challenging, for example, training data set, okay, to it. And let's see what's going to happen. I'm going to even let it train for 500 epochs, not for 200 as we have done before. All right, so let's get started. So as you guys can see here, I don't want you to be confused. Here we train the model twice. We're going to train it first using our simple model. And then we're going to train it after using, more neurons, okay? All right, let's do this. So we're going to run this first. We're going to skip this section. We're going to keep forward just to see how the network performs. The simple one performs first. After that, we're going to go back. I'm going to skip this. We're going to run the more neurons one, the kind of advanced one, and see what's going to happen. All right. Again, model equals sequential, okay? And then we're going to add to our model, simply. Again, dense, fully connected network. And then our input dimension is 2. Our activation function is sigmoid, okay? Actually, we can simply delete this because we're going to have it again here. And afterwards, we're going to compile, do the model.compile. We're going to use our loss function, going to be binary underscore cross entropy because we have kind of binary outputs. And auto optimizer, we're going to use Adam optimizer. What we're going to pass, we're going to pass our X train scaled, which is our scaled input, our Y train, which is our target class. Epochs, we're going to set it to 500, and verbose, we're going to set it to 2. All right, let's run it. And you guys can see here, that's how the network is, is being trained. All right, obviously we're going through like 500 epochs, and you would see there's actually performance. It's the loss is changing, is going down as we move forward, which is good. And then it stopped at epoch 500. All right, again, we're going to skip this because that's kind of the advanced form of the network, a multi-layer network. All right, let's run model.summary. That will tell me I have 3 adjustable parameters, 2 weights, and 1 bias. And let's do predictions. So we're going to do model. That's our train model. Okay, we're going to apply predict classes, and then we're going to use X test scaled, which is again the testing category or testing data sets, which is again our 25% testing. The model will run again. We'll do forward run. We'll generate our predictions, and that's our predictions Y predict. All right. Here we're going to apply again our confusion matrix. We have done that before. We're going to repeat again here. From sklearn.metrics, we're going to import our classification report. Okay, we haven't discussed that. We're going to show you what it is now, and we're going to show us as well our confusion matrix. So what we're going to do, they're going to run our confusion matrix. I'm going to send our true class, which is Y test, versus my predictions, which is Y predict, which is simply my output here from the predict classes method. All right. Afterwards, what we're going to do, we're going to plot our heat map. So SNS seaborn.heatmap. We're going to plot simply our confusion matrix, and we're going to plot our annotation as well, just to show us the actual true numbers. Okay. All right. Let's run it. So we're on prediction. Here, this is our confusion matrix, and the results are, well, they are. So we correctly classified 161, 169. We misclassified 20 and 25. All right. Let's plot the classification report. So actually it's not bad. We actually reached 88% kind of precision. This is kind of, you know, like a summary of our accuracy throughout the testing. All right. What we're going to do here, again, we have done that before. I'm going to walk you through it really quick. We're going to plot kind of two maps, okay? One for the training and one for the testing, all right? So here, you simply, again, we're going to use the exact same code. The only difference we're going to specify, we're going to specify X train scaled and Y train. That's simply showing them what we're going to be plotting here is our training data set. We're going to do the exact same thing here, but instead we're going to use X test scaled. And that's why we're going to be plotting the title. We're going to be testing data set. That's pretty much it. Again, it's kind of a grid that shows us our performance and our boundary line as well. All right, let's run it. All right, and that's what we have got. So as you guys can see here, since we didn't add like different layers in there, and the network's pretty much, you know, has like linear operation. So that's why the network predicted there is a linear line. That's the best it could find. But because our classes are actually a little bit more challenging, we misclassified some samples here. So the boundary said we should be in the green, however, we classified them as red and vice versa. So these are kind of, you know, the wrong samples that we've got. Okay, let's run it again. So that will show us our weight and biases. Again, we only have 2 weights and 1 bias because we simply have 1 neuron. And then here, we're gonna visualize the map again, but that's for the testing one. That's the testing values or testing data set. That's 25% of the data. And if you guys can see here, again, we misclassified number of samples here. And if you guys go up, you will see that these are the 25 and 20. That's around 45 samples that have been misclassified. That's actually my 45 samples that have been misclassified in here. Okay, all these samples are correctly classified. All these samples are correctly classified. These ones are misclassified. Why? Because we didn't capture the non-linearity within our model, because we used it with just one simple neuron. Okay, obviously we're not happy. We're not satisfied with the results. Let's go back and retrain our model with a more multi-layer perceptron network. All right, let's go back. All right, what I'm gonna do, again, we have the exact same stuff. Here, we're just gonna skip this. We're gonna go to let's try more neuron section, okay? All right, let's see how we build our neuron, our new multi-layer perceptron network. Model equals sequential, okay? And then afterwards, we're gonna start to add. That means we're gonna build our network in a sequential form. First step is that we're gonna add 1 layer, okay, with 20 neurons in the hidden layer. So we're gonna call model.add dense 20, and the input dimensions are gonna be 2 because that's coming from the input layer, right? So we have 2 inputs and we're gonna have our hidden layer. That's what I'm specifying now. My input to this layer, I have 2, and I have 20 neurons. And what I'm gonna do is gonna use an activation function, ReLU activation function. If you guys recall, the rectified linear units, they're actually very powerful. It's kind of, you know, the input is negative, we're gonna set it to 0, and then we're gonna go to linear, okay? It's good because it keeps the gradients. It doesn't saturate our gradients, such as the sigmoid function, and it's actually very powerful. We're gonna see how can we do it then. And then afterwards, we can add again another layer. So here I'm just, you know, just having fun. You know, let's add, you know, whatever layers we want. We add, let's say, 3 or 4 hidden layers. So we add another layer, 20 neurons. Again, dense. It's very simple to add, you know, like change the architecture of the network as whatever we feel like. Activation function ReLU as well. And then again, we added another network, again, another layers. You guys, again, here I'm just trying, you know, like stuff up, making stuff up. And then model the last layer, that will be my dense layer. Again, that will be linked to the output. Again, we have 1 output, so we have 2 inputs. We have several hidden neurons, hidden layers, and we have 1 output. They can tell me are we class 1 or class 0. And that's why in the output layer, we use a sigmoid function, okay? Because we need an actual saturation to play into, to be effective here. We wanted to classify classes to either 1 or 0, which is perfect for sigmoid function. All right? And then afterwards, these are exactly the same as we have done before. Model.compile, we're going to use the loss function binary cross entropy because we have binary output. Optimizer is Adam optimizer. And then we're going to model.fit method, we're going to apply it to our model using the X train scaled and Y train through 500 epochs, and verbose we're going to be 2. All right, let's run this. So it's training. Okay, as you guys can see, the loss is actually going way down now. That's actually pretty good. So see, why? Because the network is very powerful. We have a lot of neurons. That means, you know, more powerful brain. And just imagine if you have like, you know, a supercomputer, you know, what you can do with this. It just, you know, it's magic. You can just add, you know, you can build an actual physical, you know, like brain that does, you know, like a very powerful classification, regression, whatever you want with your network. All right. Let's see model.summary. Okay, that's pretty interesting. So these are the kind of our different layers. So we have dense layers, okay, of, let's say 20 neurons. All right, so we have here 60 parameters, and then we have again another layer of 420. So when we say 420, because we have 20 that's passing to 20, which multiply them together is 400, in addition to our biases. That's why you will see there is 20 biases as well. So that's the first one. And then from the next hidden layers to the next one, okay, you will come up with 420 as well. Again, 400 weights and 20 biases, 400 weights and 20 biases. And then the end, you have, you know, the last layer connected to the output. We have one neuron, we have 20 inputs, right? That's why you have 20 weights and you have one bias. And that's why you have 21 here. Sum them up, you come up with 1,341 total number of parameters. Okay, pretty good. Obviously, that's kind of an overkill to our case here. Here, I'm just showing you kind of an example, and then next example, I'm going to have another practical example that can, you know, take us a little bit further to classify a little bit different kind of inputs. All right. Okay, let's see how can we do again the exact same stuff for the confusion matrix. We're going to do the prediction, and we're going to look at the confusion matrix. Actually, it's amazing. As you guys can see here, we actually done pretty well. All samples are correctly classified. We didn't misclassify any samples, which is perfect. All right, let's plot if you guys recall, this is the confusion report that we had before. It was showing 0.88. Now, it's obviously showing 1. We're doing great. Let's take a look at the actual boundary, and let's see how did it come up with our boundary. Let's plot it. All right, perfect. As you guys can see here, it's, you know, it became way smarter. And it came us, okay, let's go there and let's, you know, like go down and, you know, and draw an actual little bit more complex boundary. And that's how we classify the samples, which is perfect. And then here we show us all the weights and the biases. Obviously, we have way more weights and way more biases, okay, because we have a way more complex network. And that's for the testing data set. Okay, and we actually did like pretty well too. So that's pretty much how can you train a multi-layer perceptron network. And that's all what I have for this section. I hope you guys enjoyed it. This actually was a lot of fun. In the next section, I'm going to build, again, another multi-layer perceptron network, but to classify different kind of, you know, like form or shape of data sets. All right. Hope you guys enjoyed it, and see you in the next one.